Welcome, everybody. Very happy to have you all here and present our speaker today. We have with us Professor Grossniklaus, who is a professor here at Uni Konstanz and part of the cluster from the beginning. Michael is originally did his academic, has his academic origins at the ETH in Zurich, then did a couple of postdoctoral stays in Milano and Vienna, and then pretty quickly came to Konstanz and decided to stay here ever since. And we are very, very happy to have him finally here and presenting on why you should care about query optimization in databases.
Why do I think people should be more interested in query optimization and kind of in the systems and the tools that computer science has to offer? So from my perspective, what I see is data are everywhere, and this of course is because we have digitalization spread, so there are sensors in all devices, there are autonomous and learning systems that also produce data, and of course this is kind of a blessing, but of course it's also a problem, because on the one hand and I think that the cluster is a very good example for that. This opens up the possibility that we have evidence-based answers to existing questions, but we can also derive new hypotheses from the data that we collect. But it also brings challenges. So if we have a lot of data, we need to be more clever about how we work with that data. What is the fastest method to get an answer? How can complex processing tasks be parallelized or distributed over several computers? We know that for the longest time in computer science, in hardware, we had this Moore's law where every 2 years processor speed would essentially double, and now this is no longer the case. Now what's happening is we're getting more cores, we're getting more parallel computers. Yeah, so I was talking about the possibilities of having a lot of data, but also some of the challenges, and then of course also how can a large data set be reliably distributed and stored. We don't want to lose the data. Now, one number that I find impressive and somewhat scary is, and now of course I'm in Zoom and no longer in the presentation, is this number where the US Department of Transportation estimates that by the time we have all cars are self-driving, we get 25 petabytes per second. So that's not something I can fit. I cannot fit 1 single second of that data on my laptop. So if you were to ask me today, Michael, but how do we deal with that? I would say I have no idea. Now, what we see here is kind of two things. We have, and again, I think the cluster is a good example why there's an opportunity here, because you have two very different profiles of people. You have people who are actually interested in actual questions. They are actually interested in learning from data, in deriving new hypotheses from data. And then you have people like me who are interested in how can I make things go fast and how can I scale things. And traditionally, typically, the way we do that in computer science is by providing tools that allow the people who are interested in the applications to really focus on what their business is, like biology, like economy, like psychology, and behind the scenes the system takes care of all of these things. And database systems are, I would say, a very good example where this has worked really, really well. The first database systems were developed in the 70s, and they're still around. They're still being used. And so the promise, and forgive me that this is a bit grandiose, the promise here is the human dreams about the possibility and the system worries about the challenges. Now, of course, there is some small print here. Of course, this only works if there is some contract between the human and the system. And so in order to illustrate what this contract is and why that then opens up a lot of possibilities and why this has to be in this way, I would like to very briefly go into how databases actually work. And because another thing I'm interested in, apart from making things go faster and scale them out, is Lego. So this is somewhat based on a true story. At one point, actually, Johan came to me in my office and said to me, Michael, do you know this Millennium Falcon? And I said, yeah, the kids of my friends have this Millennium Falcon, this Lego Millennium Falcon. And he said, no. There is a really, really big one. And I said, what? And so I looked it up, and there is this Millennium Falcon that has, at the time, had 5,200 pieces. And so I immediately said, I want this. But then, of course, when we talked, it was no longer available. It originally came on the market in 2007 for, I think, roughly 500 euros. And at the time, if I wanted to buy that used or even new, it would have been 8,000 to 10,000 euros. And so I said, it's clearly not the road I'm going down. So, but then another thing that I discovered is that there is this website Bricklink where you can buy individual bricks. So I started looking at what bricks do I need, and then I started to fill up these boxes, and at some point, inevitably, I got myself in a huge mess that I noticed by putting bricks into the box that they were already there. And at that point, I thought, okay, it's a little bit embarrassing that a database professor tries to make sense of the world with Excel. Maybe I need to change something here. So basically, I thought, databases are all about getting answers from your data, and so if I can datify that, and then I can ask the question, can I build that? So how would I do that? Well, of course, I would start with a list of the sets that Lego has. For instance, apart from the Millennium, there's also a Death Star, there's also a Red 5 X-Wing Star. So you notice that there's a third thing I like, which is Star Wars. And then, of course, Lego has all these pieces, the 2x4 brick, the 2x2 brick, and so on. They all have numbers. If you have really good eyes, you can turn them around and actually read those numbers. But if you don't have good eyes, you can just go to the web. And then you need to make sense. You need to know which parts are in which model. And apart from knowing that a part is in a model, you need to, which is what I have here. So the model, the Millennium Falcon, needs the 2x4 brick, but then I also need to know in what color and how many times. And you can see, for instance, here with the Death Star, it also needs the 2x4 brick, but it once needs it in dark bluish gray 22 times and in light bluish gray 45 times. So that's how you kind of keep track of this information. But then, of course, that is very static. That doesn't answer your question. So now we need to think about, well, how do we compute with this data here? And this being a table, which is a two-dimensional thing, very obvious things you can come up with is, well, you want to select some of the rows that you have in this table. And because we like to give ourselves the air of being scientific, we say, okay, selection starts with an S, so what's the Greek letter for that? Sigma, so that's how we're going to denote that operation. And if we have the set parts and we want to know which parts are used more than 30 times, which are those parts there, we can compute a new table that is the selection num larger than 30 on set parts. And I will talk a little bit about that, but this, of course, is very important that we apply an operation and we get an element of the same kind. So now we have rows, then the next obvious thing you can do is columns. So if you want to know what are the identifiers, so just the set identifiers of the sets of the parts or Yeah, what are the sets that have a part that is used more than 30 times? You take the table we had before, and we can just apply another operation to get those set identifiers, and we call that a projection, and because it's a P, we have a P as a letter, and so you get this. And you can also see something happened here. We have fewer rows now because we are working on sets, and sets cannot have duplicates. The last one I want to talk about, there are many more, but the last one I want to talk about is we saw that we had multiple tables, and there is also, of course, we need to be able to combine these tables. And so if we have the set Millennium Falcon and we want to know which pieces are actually in there, we need to combine these two tables, and we call that the join. Now, apparently the Greek alphabet doesn't have a J, so we took this bow tie symbol, and what the join does is it computes a new table. It has all the attributes from the first table plus all the attributes from the left table except the ones that overlap. You can see there is not a repeated SID here, and then it goes and looks for matches. So it takes this SID there and matches it with the one over there. And it kind of constructs these tuples. And now we have now we can see, okay, Millennium Falcon, which pieces. So what have we seen so far? And why is this a good idea to do it in this way? Well, so far we have seen two things. We have seen what we call a data model, which were the tables. So the data model tells us what the data looks like. And we've seen these operations that are orthogonal building blocks. I say orthogonal because I can apply an operation, I get another table, I can apply another table. And basically what we have here with these two things is we have an algebra. Where the elements of the algebra are our tables, and the operations that we've seen are our operators. And it is true, it is a closed algebra in the sense that if I combine two tables, I get another table, not a dog. So you know this. And there is a strong analogy to arithmetic, where in arithmetics you have the numbers and we use tables, and in arithmetic you have plus, minus, divided by, multiply, and so on, and we have selection, projection, join, and so on. Now, why is that great? Well, because if you have an algebra, you also have rules, equivalence rules. You, for instance, know that 1 plus 2 is the same as 2 plus 1. You have associativity, you have distributivity, all of these kinds of things. And the same is true for our algebra. So with these rules, you can transform expressions, you can simplify expressions. We know that from mathematics. And so what we can do is we can look at different ways of computing the same thing. And this is a very powerful thing if we want to build a system that finds for you the best way of computing something. That system needs to be able to figure out what are the different ways of computing that. And it needs to prove, or somebody needs to be able to prove, that these different ways are equivalent. Because if you ask for who's the richest person in Germany, and they tell you, and the answer is the heaviest dog in Iceland, then that's not the question you were asking. And maybe it's a question where I can compute the result more efficiently because there are not so many dogs in Iceland, but it's not what you ask. So it's really important that we can compute it. And we can actually push that analogy to arithmetics. We can push that farther. And we can ask ourselves if we have an expression like 10 times 4 plus 5, which in computer science we then usually represent as some kind of tree-based structure where we would evaluate that from bottom to top. So 4 plus 5, and then we would replace that by 9, and then times 10. Now, there's two strategies how you can do that. You can do it in this way. You can look at the parentheses, replace that by 9 and do 10 times 9. But you could also use distributivity and basically do 40 plus 50. Now, I don't know, I don't want to speak for you, but when I look at this expression, in my head, I do the first one. Now we can come up with another expression, which is 7 times 10 plus 3, which looks exactly the same, represented as a tree. And again, we have the same two strategies. We have 7 times 13, and we have 70 plus 21. And now, my head changes what the strategy is to evaluate that expression. Because 7 times 13 is a lot of work in how my brain is wired. But seeing that there is a 70 plus 7 times 3, I don't need to think about 70 plus 21 is also easy. So now I switch to the second. And the important thing is, this does not depend on the structure of the expression. This depends on the data you apply and this is exactly the same in query optimization. There are always different strategies how a result can be computed, and there are simpler, i.e. cheaper, and more complicated, i.e. more expensive ways. And the cost, as I just said, the cost of a strategy does not depend on the structure, it depends on the data that you're. Now we're at the point where we have something really, really powerful, and now we need to think about, well, how do we propose that? How do we give that tool to a user? So how do we build a system like that? And of course, once we come to that point, we need to think about, well, how will computations be expressed? How do we actually formulate those questions and give them to a system? And here, it is a little bit important, or I want to talk a little bit about how we can formulate programs, what different strategies there are, and why databases use a specific strategy here. And the first thing is, if I have that table set parts from before, and I give that to you, say, as a CSV file, and I would ask you to specify a program that finds the colors in which this part 303 is used, you would very likely come up with something like this, where you would say, okay, I open the file while I'm not at the end of the file, I read a line, I somehow parse it. If it's a CSV, I need to split on the commas. Once I parse it, I know where, at which position I have my 303, and if the 303 is, then I add this record to the result, which I have initialized to some empty set, and in the end I return the result. So this is what we call an imperative program, but there's also a way of declaratively specifying that, and the corresponding declarative program is just I have this table set parts, and I am interested in the color from this table set parts where the PID is 3003. Now this is not only much shorter than this, but there are also some really, really fundamental things that are different. If you think about what do you specify here, and what do you specify here? And you can actually argue in this sense that I made before, that there are people who are interested in actually answering the question, and there are people interested in how would you do that physically on a computer. Here, you're actually asking too much of the people who are interested in the question, because you don't just ask them to specify what they are interested in. You also ask them to specify how it should be computed. And so this is actually, it specifies what to compute and how to do it. This one doesn't specify how to do it, it just specifies what to compute. And of course, this now makes it very obvious that in a situation where the how to compute it can depend on the data you have, this is not a good idea, because here, if you want to do something like that, where you switch the strategy how to compute something, if you hardwire the strategy, you lost. That's not going to work. And so something like that is a much better approach. And think about this. I mean, if you're think about how obvious it is that this is not always the best strategy. Think about a textbook. If I ask you to find all the page numbers where that textbook talks about recursion, I mean, who in the room is stupid enough to start on page 1, read everything, and every time we see recursion, we note that no. We don't do that. We flip the book around. We check if there's a table, if there's an index. If we have the index, we immediately have the result. If there is not an index, we flip the book back. We look if there's a table of contents. There's always different strategies how to do that. And all of these strategies, because computer science is not rocket science, it's usually inspired by what we do as humans. Of course, we have indexes, different types of indexes in a database system. But also there, it's not always obvious whether or not the database system should use the index. That again depends on the query. So the whole thing then becomes a kind of matter of abstraction, and you have these two extremes. You have down here, you have the hardware, which is a very simple but time-tested hardware. We often talk about the von Neumann machine, which has a CPU, RAM, etc. And up here, you have a person with question, ideas, and dreams. And in between lie all these, I call them artificial problems, because from the perspective of the person who wants to get an answer, these of course are artificial problems, but to me as a computer scientist, these are the exciting problems. So how do I parallelize? How do I distribute? How do I do memory management? How do I compute things with the maximum precision? And nowadays, what is also important, how do I do it energy efficiently? And optimization is kind of a term under which we throw all of these, if we are trying to improve in terms of runtime, so making it go faster, or task-based performance, making it more precise. And now the question is, whose job is that? Who should do that? And that then brings us to different programming languages. If you're using a programming language like C++, the job of the human comprises a lot of these things, because you are at a low level of abstraction. If you use something like Python, you're a little bit better, but you still do a lot of heavy lifting, because it's still an imperative language where you specify a lot of the how it should be computed rather than what should be computed. And if we look at databases, we have SQL, where you only have to talk about the what, and the how is completely decided by the system. And so sometimes you hear computer scientists talk about low level of abstraction, high level of abstractions. That's usually what we mean about that. Now, I already mentioned this language, SQL, and SQL is an algebraic language. And I think algebraic languages are absolutely awesome, because they nail this trade-off between the human and the machine. in the sense that the human doesn't want to concern himself or herself with how this is actually computed. We have better things to do. And so these algebraic languages, they support the specification of very complex computations, i.e. the what, and they leave ample room for optimization, so to make it go fast, the how. And I was talking about this algebra before, and the SQL is basically just an ASCII version of the relational algebra, where we have the projection, which is the select clause. Just to confuse people, we didn't call the selection select, but the projection. That's just to annoy people, because I mean we want to make life difficult, so that people think we are rocket scientists. Selection is the where clause. Something like join, you just write natural join in the from clause. And there are other operations from sets. And so the example before, where I joined set and set parts and selected the Millennium Falcon, it doesn't really have a projection, so we write select star. But then you see sets natural join set parts. That's basically this, and the select description Millennium Falcon is as promised the where. Now we can start to put this all together. And once I've done that, I will actually give you a couple of examples why this is super important. So we start with a declarative query statement, the one that I just had before, which again specifies what we want to see and not how, and the promise that the database system does is, don't worry about it, we'll find the best way, and that's kind of our holy grail. That's what we're after in research. So once I have that, of course, I can put it at the level of the relational algebra. And once I have the relational algebra, I can start to play around with that. I can say, okay, one rule that I can apply is if I have a selection that only applies to one input of this join, I can push it inside the join. I can do the selection first before I do the join. Why is that a good idea? Well, the join, as we've seen before, needs to compare everything from that side with everything from that side. If we filter that side first, that's usually a good idea. And then another thing I can do, I can switch that around, the join commutes. Why is this a good idea? Well, there are some implementations of join operations that can use an index on the right side. And so if we have an index on description, we need to move that over to the right side. So now we're basically at this point where we were before. We had our numbers. We had the different ways of computing it. But then I said, look, in my head I do this, and for the first expression, and in my head I do the second for the second expression. We've not talked about how we do that in systematically. Now we need, for each of these expressions, we need to know which one is better. And so that brings us into the last and fourth step, which is cost estimation, which basically is a substitute for my head saying, okay, I like this way of this strategy better or that strategy. And there has been a lot of research about different cost models. I'm showing here one of the more simpler one, which is the C out for a table or a plan, which is just 0 if the T is a leaf, and otherwise the cardinality of T plus recursively the cost of the two join partners. So in order to understand how that works, we can look at the plans we had on the previous slide, and again we draw them as I did for the algebraic, for the arithmetic expression. I draw them as these trees. And so the first one that joins S and SP and then thus the selection would be this tree, and I actually looked up the number from the Lego database. So we have 13,000 sets, roughly 700,000 entries here. If we join that, because of course it just adds for every of these rows to which set they belong, we get the same, and the selection for Millennium Falcon gives us 240. So what does that mean? The Millennium Falcon has 240 distinct pieces. The other one where we push the selection down here, of course, then selects 1 here and 240, and this one is just a mirrored example. So if we apply this cost model, we get a cost of roughly 700,000, because we only look at the join nodes, and for this one we get 240, and for this one we get 240 as well, and then we can choose this plan and execute that plan, and that's actually not a bad plan. Okay, so this is query optimization. This is what we do, and maybe now a little bit more specifically, what are some of the things we work on in our group? So, and one big area of work that we do is cardinality estimation. Why is that important? Well, you just saw I came up with all of these numbers. How do we know this number 240, and how do this number we can actually know, but how for this join, how do we know this 240, that this is the result? And this is important because knowing this 240 was the basis for making the decision to choose that plan. So that's an important thing. And this is basically what cardinality estimation does. And I've currently one PhD student who looks at just like predicates that look at string matching. So if you have like something like the set name needs to contain Millennium Falcon, this needs to be a substring. How do you estimate how many rows that will select? We also look at general learning-based cardinality for full SQL queries, and we're also applying traditional and machine learning-based cardinality estimation to Cypher queries, which are graph queries. Then we're also looking at the overall process, the query optimizer as a whole. Query optimization is NP hard, so this is a tough problem, and so we look at efficient algorithms for search space enumeration, but we also apply machine learning, kind of trying to predict the best plan. And finally, I think we do a significant portion of our work in non-relational systems, so systems that don't store tables but other things. So one thing we do is query optimization for graph databases. We also look into index structure for graph databases. Now, after the retreat and with the PhD of Johan, who is here, we want to see whether we can apply these same mechanisms to trajectory data. So I would just very briefly like to give you some kind of ideas of how much room for error, or to flip it around, how much room for performance improvement there is in this area. And so one thing we did a couple of years back is we looked into nested queries. In SQL, you can write nested queries where you have some attribute and then you compute a set and you check whether this value is in this set. And so if you write this query like this and you use a 10 gigabyte database and Postgres, which is an open source database system, you get a running time of over 24 hours. Now, it actually turns out you can write the same query in this way, without this subquery. You can rewrite it so that the subquery goes away. If you do it in this way, then you get 32 seconds. So it's a huge gap. I mean, this is not enough time to drink a coffee. The other one is enough time to drink at least one coffee and do a couple of other things. And of course, this always bugged me, because I know that many database systems actually out there are bad with these nested queries. And I really like this idea of separation of jobs. The user specifies the query and the database system finds the most efficient plan, which clearly here is not the case, because the user did their job in both cases. They specified a query that computes the desired result. They just use different specifications. And so there's something behind the scenes that doesn't work. And so what we did is we kind of looked at that, and it actually turns out the problem is that this relational algebra that I showed to you before, it doesn't have a notion of nested queries. You cannot express these algebraically. And so we thought, okay, what are we going to do? And so what we actually did is we uncovered an algebra from the 80s where people, Mark Scholl of all persons, they were very interested in having tables where you could have nested tables, so where as an attribute you could have a subtable. And they developed this non-first normal form, NF squared. And I'm not interested in these nested tables, but I'm interested in this algebra, because this algebra, apart from having nest and unnest, which we don't know, they have a generalized selection and projection, which allows us to express these nested queries. Because in the selection, that's the where, and the projection, that's the select. That's where you can have nested queries. You can also have them in a from, but there they are not an issue. And so we took this algebra off the shelf, and it enabled us to write a nested query in this algebra as such. And then what we also did is we went to the literature and looked at what did people propose in terms of techniques, how to optimize all of these nested queries. And we actually derived equivalences for this algebra, and we also proved that these equivalences were equivalences, because in the domain of nested queries there has been quite some charlatans with transformation rules that didn't actually work in all cases. And so there is a survey paper that kind of classifies them with letters. So we have these rules, and I don't think I want to go into too much detail. But with this rule, you can basically remove the nesting and get to that second much faster formulation. And the nice thing about, because this is an extension of the relational algebra, all the previous equivalences that the relational algebra has remain valid. So if we see something like a cross product together with what do we have, part and supplier, together with a join predicate, then we can transform this into a join. So does this help? And so we looked at different systems with nested queries. Postgres Hyper is from the TU Munich guys in memory. DBX, DBY, DBZ. We can never put the names of database systems because that's in the end user license agreement. The so-called DeWitt clause after David DeWitt from Madison, Wisconsin. Every database system has in their clause, if you do performance measurements, you're not allowed to tell who is who. I cannot put that in the paper, but I can say Microsoft SQL Server, IBM DB2, and Oracle. And so this is some of the performance benefits we got here. So Postgres had a lot of timeout, so we then go to 100%. DB2 is a tragic case of doing a lot of things right and then falling down at the last minute. Actually able to rewrite the entire plan, but then the cardinality estimator messes up, and probably a bug. SQL Server is quite good. Hyper is super fast in any way because it's an in-memory database. Now, okay, this looks good, but then the question you should always ask is, what do we pay for that? And so with optimization, you have to look at two things. Does the optimization process take 700 years, and then you get a query that is 2 seconds faster? This is not an issue. I already had the optimization times on the previous slide. They were already in there. Then the next thing you need, which is very important to these vendors, is, do we need more memory? Because do people need to buy in a more expensive server? And so we looked at all of these queries, and there was just one that had significantly more memory, which was a bug, but we only discovered that later on. It's in the paper. Now, the same thing, you can also do that with graph databases. In graph databases, you have this Cypher query language, where here I have a movie database, and I'm looking for two actors, X and Z, and they jointly star in a movie Y. And X is Al Pacino, and Z is Robert De Niro. And you can come up with this execution plan, or actually that's Neo4j, open source database system comes up with that. It looks for the node Al Pacino, then it expands from Al Pacino's to Y, and then from Y to Z, and then it looks at, no, it's actually going the other way around. It starts with Robert De Niro, it expands out, and then it filters for. And if you look at this graph, what that means is, you start with Robert De Niro, you expand to all neighbors, and then you expand again to all neighbors of that. And now in all of these blue nodes here, you're trying to find Al Pacino, and then this is your result. And already visually you can tell this is not a good idea. It's you're interested in very little data, and you have this monstrosity in. And if you actually then look at how much interaction this requires, how much database hits they call it, this is the number you get. So a much better plan would be to do that, to look up both of these actors, expand to all the movies, and then do an intersection of the movies that they starred in. If you do that, you get 90 dB hits, which is 90. And so you can execute this plan, but Neo4j doesn't do that. So you can again ask yourself, why not? Why doesn't it do that? And from what we know now is, either this plan doesn't get considered, or it's misestimated as more expensive than the previous one. So our hypothesis is it was not enumerated. So what we did is, again, we came up with an algebra. You come up with a data model, which is your property graph, which I won't go into the detail, and then you come up with an algebra. And already, don't be surprised, everything we do is an extension of the relational algebra, because the relational algebra has worked for so many years. So, of course, you take the relational algebra, selection, projection, union, difference, join, and you add some specific node, like get me a node, get me edges, expand out, and so on. And you can define all of that based on your data model. Then you also have a specification of what they do. You can come up with equivalences, what expressions are the same, and then you can actually take such a statement like the one, rewrite it in the algebra, transform it a couple of times, and you would get this alternative second plan that then does index lookup on both sides and a join in the middle. And of course, what you can also do is you can give these open source freaks that just code until there is no more power coming from the outlet. You can give them that and tell you, look, actually for what you write as a query, I can now specify what that means and what that does and what the correct result is. And so if somebody else would implement a Cypher query processor, which is of course what they hope, that this gets to be an industry standard, then there is some description of semantics. So to conclude, what challenges lie ahead? And I have this very scientific chart here, where we have time, which starts somewhere and points to the future, because that's always good. And there's two things I'm kind of interested in. Is one, on the one side we have data. And data can be a stack of needles, where it's not really difficult to find a needle, or it could be a stack of hay, where it's difficult to find a needle. And with processing, you have easy peasy up to rocket science. And so what has happened over time is that there has been an increase in the type of data we have. These relational systems started with business data, then came the web with user-generated data, and now we see a lot of scientific and sensor data. And on the other hand, you had like these SQL things, what the language was designed for. Then we started to go into large-scale analysis, and now we do hypothesis generation and confirmation. And we can see a little bit that the systems with which I'm involved, there's a gap that starts to emerge. Now, one thing I talked a lot at retreat was, so how do I think about problems? What is an interesting problem to me or to our group? And again, I'm using the same two super scientific dimensions of processing from easy peasy to rocket science, and data from stack of needles to stack of hay. And this kind of gives us 4 quadrants. There is this quadrant, which as of today, with basically everybody knowing some programming language in the cluster, I can say without loss of authority, just do it yourself. If you have simple processing, then nice data, do it yourself. There's this, once the computing gets more difficult, call the algorithmics group. You can also call us, and if we don't like it, we send you over to the algorithmics. If you have complex data, call the database group.
I'll call you.
And now we're really talking. Now it gets really interesting if we're in this corner up there. And I mentioned trajectories before, and in my opinion, that's I put a cloud, so to rain on our parade. That's where I think all of these trajectory problems are. And you can also see that because both the algorithmics group and the database group have a keen interest in this topic, and you can see that there is. Now, from my perspective, why do I think trajectories are interesting? So, for trajectories, it's not obvious what the data model is, and I would even go further, and I think there is not one data model for trajectories. Of course, you could kind of represent them as a table where you give them some ID, you give points, and you give a timestamp. You could kind of, if you map them out into the world, you can kind of see, okay, I have this blue trajectory, this red trajectories, I have different regions, and you could kind of say, okay, I plot it over time, and I say, okay, the blue trajectory in this interval was in this region, and then it moved over into that region, and here we have another trajectory that starts in region E, moves to region C, and then comes back. And of course, you can also look at it like a graph down here. And another thing, so we have these different representations, and that's kind of step one. Again, what is our data model? What are the elements of our algebra? But then what we see is you also have, of course, your operations. What are our operators in the algebra? And you can see that there are operators that assume the trajectory to be a time series. They assume the trajectory to be a graph, or there are things you can do again on a tabular format. But But these operations sometimes require or heavily benefit one of these representations. So just saying, okay, these are kind of equivalent, I do everything like that, and then that's not going to work. So you might need to think about a system that can kind of represent the same object in different ways. But then, and I think this is super exciting, trajectories are often just a kind of backbone on which you hook other information, or you need other information, you need context to understand what's going on. And this actually for these kind of, where trajectories are routes, this has actually already been understood and is called map matching, where you actually take the trajectory and you look at the physical environment in which it was tracked, and you notice, okay, it's probably not tracked correctly because the road goes down here. There's a lot of work of kind of fixing trajectories. I mean, there might also be problems with sampling, that you have a point here, you have a point there, but clearly the trajectory cannot go through that building. It's just because you didn't sample at this point where we were actually at the corner. But then, of course, in order to understand this, you might see, okay, that person or car was moving very fast, but now sometimes it doesn't move fast. So what happened? You need additional information. You need the information. Was there maybe a traffic jam? Is there a point of interest? Did they get out of the car and look at the Colosseum? Stuff like that, which is something that to me is new and interesting, because the more ways you have to look at it, the more different strategies it will. Do I come from the traffic jam to the trajectory, or from the trajectory to the traffic jam? I mean, maybe for us conceptually we come from the trajectory to the traffic jam, but that doesn't necessarily mean that this is the best way of processing the data. Maybe it's much better if you have that hypothesis to look at the traffic jams and then at the trajectories, which again is all of this turning around and working with the data. So this is kind of what we want to do with the PhD of Johan, or a subset of is probably Johan's. I'm also thinking currently of writing a joint proposal with Sabine on this, because I think there's a very clear line what we are interested in and what she is interested in. Because one thing I have not talked about in this talk is what are the algorithms with which we actually implement these operators. I have not talked about different ways to implement the join, different ways to implement the selection, different ways to do a projection. There are more join algorithms than you would expect, and they are all optimized to some scenario. And so this to me is the clear line where an algorithmics person, they would be interested in developing these, what we call physical operators. And then we could use these physical operators, and by this idea of an algebra, of a cost model, of equivalence rules, we can combine that into a system that then actually finds these execution plans. So that's my next project. Maybe in the Christmas vacation, Johan did a nice job in writing a PhD workshop paper for one of our major conferences, which is 4 pages. So the only thing I need to do is add another 16 and talk it over with Sabine, and then let's see what happens. Okay, that's what I wanted to talk about today. I had no idea for how long I should talk, so I just. Is it okay? So I can go on and talk about other things.
Thanks a lot, Michael. That was really fascinating, even for a non-computer scientist. So thanks a lot. Are there any questions from the audience? Come on, we have a room full of computer science people.
So thanks for the overview. You didn't speak much about, let's say, or you said like these trajectories are embedded in a context, but I guess the question that also arises, there are a lot of questions like within trajectories, like all these physical and behavioral things. To what extent, like, does a database of the trajectories also need this kind of meta information about all these things are on top of just the trajectories? I mean, you can store everything, of course, yeah.
I would actually say the trajectory is the meta information, and then I mean, there's two things I think that are interesting with these trajectories. One is this kind of augmentation with which I see something like fixing the sample rates to make sure that and so I think that is one thing you can do, and then the other thing is this contextualizing, where you look at the environment, and of course, if you think about something like a traffic jam, that's actually something where your context is other trajectories, because you see all these trajectories that are at the same time, at the same point, and slowing down, and yeah, so I think this is super interesting. This kind of to kind of think about that in a database way, where we're always I mean, when I talk about selection, projection, join, these are not operations that are specific for a domain. We're always after these general things, and I think already with this map matching and this playing with sampling rates and stuff like that, these are things that people do in a specific domain, mainly looking at, I mean, we look a lot at taxi data and stuff like that. But where you can already see that this is kind of just an instance of a general problem. And so far I've seen two, this kind of augmentation and contextualizing.
So I've actually two questions. So one is probably a naive question for somebody that doesn't know much about query optimization. So I actually believe that is an NP-hard problem, because I guess you can formulate as some kind of global mixed integer bloody problem where the global solution would be kind of like a fundamental capacity, right? Like you give me a certain task and ask me what is the best kind of configuration or the fastest configuration to answer this task, and that would be the global solution, right? And that is very hard to get. But then I was wondering, like is there anything known? Because sometimes you can do like approximate algorithms, right? You could probably come up with a query structure in a greedy fashion, where you say, like, each time I add something to my configuration, it is locally good. And then I could hope that, by doing that, I come actually very close to what is the best. Because that would be interesting, because otherwise, like I'm actually wondering, like, how do you compare, like when you evaluate like a query, how good it is? Like, how do you compare that? Of course, you can say it's faster than some other candidate, but how do you know how far away it is from the fastest that would be out there somewhere? Huh?
So maybe starting with the second question first, we cannot actually. I mean, I often joke in my query optimization course. I joke about that it's not query optimization; it's query disaster avoidance. So the hypothesis is that by staying as far as possible away from really disastrous plans, you end up with something reasonable. But the database system cannot know which is really the optimal query, because we rely on this cardinality estimation, and we only know the real cardinalities after we execute a query. Then we know it for that specific queries and all its sub-expressions. But this is then again a very limited view of the entire search space that we have. And And so, we actually did that experiment with, I had a PhD student who worked at SAP, and he actually changed the SAP HANA optimizer to give him the top 500 plans. And then we executed all of those, and what the optimizer considered to be the quote-unquote optimal plan was sometimes very, very far down the list. And this is this problem of cardinality estimation. Now, your first question there has been a lot of work on heuristic query optimization, like greedy optimization. But then, of course, if you do greedy, you again need to come up with some kind of idea. What is a good subplan, and so people have looked into basically what the thing in relational query optimization. The thing that makes it NP hard is the join ordering, deciding in which order to join tables together. Do I start with these two and those two, and then I join the result, or do I start with these, then I join one, I join another one? I mean, that's where the complexity comes from, because there's so many, due to associativity and commutativity, there's so many ways of doing that. And so, people have looked into kind of doing that in kind of n steps, where they say I start with those, and then I get whenever you join two tables, you replace them with the joined table, you put them back into the set, you look at it again, and you go on. And there's been greedy, there's genetic algorithms. Actually, Postgres switches to a genetic optimizer after you have so and so many tables in your query. It switches to the genetic optimizer. There's simulated annealing, and I mean, just the latest in that tradition is machine learning, which I also see as a heuristic optimization, because we're kind of not going through the entire search space and try to find the quote-unquote optimal, but we try to predict which is what the plan should be. And normally we do it with dynamic programming. But it's actually not a problem that really follows the Bellman's principle. You have to tweak it a little bit to make it workable with dynamic programming. It's interesting that I think it's interesting that there are so many computer scientists, because I kind of did the talk, so I started at the very beginning so that maybe non-computer scientists could understand, but maybe they like to have a refresher once in a while.
Yeah, we already had some quite a lot of biologists also online, but they also didn't ask questions. So, but apparently everything is clear. And oh yeah, of course.
It's not like we have offices right next to each other.
so this trajectory data, so I find it also super interesting, and I was wondering whether there is, one also big hype, at least in machine learning, is about like these causal relations, right? That sometimes you have data, but behind there is some kind of causal structure that generated the data, and okay, there are these counterexamples that if you just look at the vanilla data, is actually is impossible to kind of identify the underlying causal structure. So this is not unique. There could be different structures that give rise to the same kind of data. But then, of course, like if you collect this data and you know something more than just the data, I mean, you know the system behind the generated data, you would probably want to kind of ensure that you can kind of reconstruct the causal relation from the data. And of course, this is similar, I guess, to probably the notion of time that you would. So I was wondering whether this is also something that the database community is looking at.
Well, I mean, there's very, very roughly speaking, two things that people in the database community do with respect to machine learning. One, I wouldn't say camp, but one application of machine learning is kind of what I talked about here. You take it to get better cardinality estimations and better, faster optimization, and so on. This is kind of the within. We use it within the database system. But then there is another camp that basically looks at, well, if this is our database system and we know that people on top are doing machine learning, then what do we need to do in our database system in order to kind of scale the machine learning? Scaling can always be with more data, being more precise and stuff like that. And so from what I understood, I would put that rather in the second, where you have a trajectory database and then people want to learn on these trajectories, which is not currently something that I have on my radar, because we didn't even do that for relational data.
Any other questions? Patrick?
So maybe just a fun question regarding the Millennium Falcon. Did your database eventually help you, or the Excel sheet would have been sufficient to solve the problem, the task?
Well, by the time I had the data, this is the unspoken truth of databases. By the time I had the database finished, I already built the Millennium Falcon. But I still have a huge box with duplicate parts. That is annoying. But I'm not using my Lego database, but I'm using the Lego database a lot for teaching, because it's kind of one problem I have with databases is I also sometimes give this course at the University of St. Gallen, where I talk to economy and business and banking and finance students, and so it's usually difficult to find actual application examples that many people can relate to. Another thing I do is I sometimes use football, and we did that again in the exam for the second semester course. And then in the exam review, I was talking to some students, and they just said, yeah, but I don't know anything about football, and so that didn't make sense to me. But Lego is something that is very relatable and has positive connotations. So it's a good example.
Anyways, thanks so much for coming, and many thanks to Michael for this wonderful talk. And have a nice afternoon. Thank you.